Hello, students. I really want to believe.
I do too. Hello, friends. The first and most important thing about this video, if you're following along in your workbook, which you should always be doing, is we're going to skip a bunch of pages in this section because we're not covering that content. So don't freak out if we go from one page and then we go to the next page, and that's not the next page in your workbook. Just flip forward a little bit and you'll get to the page we're talking about. There is some interesting content that we're skipping, and if you want to talk about it, we're happy to spend time with you and talk about it. But we're making some intentional decisions about what we're covering, and so we had to cut some stuff.
It's true. So I'm looking at this warm-up here, Mr. Butterworth, and it looks like we might be able to do some of the things that we've been doing in order to find some of these zeros. I'm going to tackle the first one and look at this as, so if I'm finding zeros, that's when f of x or y is equal to 0. So we got x squared minus 4x plus 4. And I know that when I look at this, that this looks factorable to me. So I'm going to factor this into 0 is equal to x minus 2 and x minus 2. That gives me zeros of x equals 2 and x also equals 2. So we really only have one that we would call a double root. The other word, fancy word we use for that is that it would have a multiplicity of 2, which makes me think of a wonderful movie that none of you have watched because Butterworth and I are old and you are very, very young.
I like pizza, Steve.
That's a reference from that movie as well. And Mr. Butterworth, looks like you did the next one.
I did. While you were talking, I went ahead and did basically the same steps. So I hope I didn't confuse the humans, but I factored x squared minus 25 into x minus 5 times x plus 5. And then I set that equal to both of those equal to 0 and got x equals 5 or negative 5, which I wrote as plus or minus 5 because I didn't have that much room. So that gave me two different zeros. Where Mr. Carlson got a repeated root, I got two different zeros.
And I'm kind of using the same idea for the next one that I'm working on, because I saw that I had something squared minus a number. So I got that something squared by itself and took a square root, and that's what I'm working on now. So I've got 3 is equal to x minus 1. That means that x equals 4. And I've got negative 3 equals x minus 1, which means that negative 2 is equal to x. So that would be for this lovely friend there.
And for the last one, we would solve it either via completing the square or the quadratic formula, which we can do if you'd like, but we're not going to do it in this video because the zeros aren't going to, that's not going to be a nicely and easily factorable problem.
It's true. And the other thing that we want you to be aware of is that the analytical approach that we did here with the algebra, you can also do using Desmos, and I've set those equations up here. And looking at like the first one, we see that we're at 2 and we only have one 0 at that location. For the one that Mr. Butterworth did where he got plus 5 and minus 5,
Got it right.
Click on those places, we can see that those x-intercepts are at 5 and negative 5. For the third one, we've got 4 and negative 2. And then we mentioned, this is being weird, that we'd have gross numbers and would have to use the quadratic formula or completing the square for. And we can see that those numbers appear to not be as nice for us.
And maybe that isn't as bad, unless they round. No, they probably round those, right?
I think those are rounded.
Okay.
But that would be an example of where one of those methods might be useful. Or again, using Desmos as a tool for this is super helpful. Ooh, I also noticed something kind of neat, that my y-intercept is in my equation where we have the plus 5 at the end. That's kind of fun. But we've talked about that before too.
Yeah, I bet that shows up in the top one also.
Ooh. It does. That's where they cross. Nope. There we go. Wow.
Way to confuse Mr. Carlson.
I know.
By the way, for those of you watching this video, if you're hearing strange noises, there are 4 small humans outside my window shouting. So if you hear them, I apologize.
That sounds normal. Okay, I'm going to go back to the main screen. All right. right. So I kind of like this title question, the did I cross the line? And that's really going to be an important characteristic and the most important thing that we're going to talk about today as far as this idea of things that are zeros that we don't see on a graph. So we're supposed to be listing key characteristics that we know about these functions. We got a number of zeros, x-intercepts, y-intercept, axis of symmetry, and the vertex. And you're going to mess up my beautiful underlining. It's okay.
I know, that's why I just made a funny face, because I wanted to give us space below the
Yep,
graphs.
that makes sense.
What you were doing was beautiful, though. I apologize.
Um,
That's why the students might have seen me making a weird face as I was moving them, because I didn't know if the graph was attached to the question.
I was about to spell zeros wrong, but then I fixed it. So we're looking for zeros.
You can spell with me, I think.
Is that one you can spell either way?
I think so.
X-intercepts, I'm going to put those real close together. Y-intercept.
Why'd you put those close together?
Because zeros and x-intercepts are synonyms in terms of how
Like
we
a
look at
synonym, but
those.
different?
Yes, it is exactly that. I pronounce the syllables funnily. So y-intercept, axis of symmetry, and then the vertex. Vertex, there we go. Okay, and I noticed this is one of the ones that we saw where we only have one. And again, we have a special name for this. It's called a double root, or has multiplicity too. And that also happens to be where the axis of symmetry is, which is kind of cool. I notice on our second one that the axis of symmetry is right in between both of those zeros, which is helpful. And the vertex also includes that number from the axis of symmetry. And the big weird thing that's happening here is that our third graph does not have zeros or x-intercepts. And it might be more accurate to say does not have zeros that show up on a graph and does not have x-intercepts. And we're going to talk a little bit more about why that happens. Ooh, no real.
That make you feel better? I'm getting a little more mathematical.
No, I was okay with that language. Because we haven't talked about what that means yet. And I have an issue with the language that we use for this anyway. I think it's dumb, but that's me. Cool.
So we're supposed to compare the three functions. What do they have in common? What is different? So the three functions, the commonalities I see is they're all parabolas.
I agree.
They all have a y-intercept.
They do.
They all have an axis of symmetry.
They do.
And they all have a vertex.
I agree.
They do not have the same number of real zeros, or the same number of graphed zeros, you could call those.
Yeah.
That makes more sense to you.
The other thing that I noticed is that the first and third graphs are what we called concave up, and the second graph is concave down. Sometimes we call these smile parabolas and frown parabolas, or up parabolas and down parabolas. Any of those words where we are mathematically is totally fine. Cool.
I think we did it there.
So the big thing that goes on here is graphically, we don't have a zero that we can see. But we can still algebraically try to figure out what's going on. And Elena and Mark here are trying to do that for us. So we have both of them setting up their expressions. So x squared plus 1 is equal to 0 in both cases. In both cases, looks like they minused 1 to both sides. And then we're told that Mark's is not correct and that Elena's is correct for a last step. I'd like to spend a second just talking about the square root as a function. And the square root asks us to think about what number multiplied by what number multiplied by itself would equal the number on the inside.
You said whatever, and I got very scared.
I was trying to think about two things at once in my head, and the other part started to come out, and that's okay. So we know things like the square root of 16, the number you multiply by itself is going to be 4.
Mr. Carlson, I thought I had to put a plus or minus in front of that square root.
It depends. If you are putting your own square root in a problem, so I think a better way to talk about this would be to say x squared is equal to 16. So then when you are taking the square root, we have to include the plus or the minus.
Oh, but you're
And
saying if I just have a square root floating in space, like this, that's not how you write. Like the square root of 9, that's just a positive number.
that's correct.
That's a fun square root also. I made a little whoop for it.
That's a very interesting square root there. So the mathy reason for that comes from the x squared. We can't tell if the x itself was a positive or a negative one. We just tend to put it with the stuff on the other side, and that gets confusing. So when we're looking at here, Elena's step asks us what number multiplied by itself is equal to -1. And we can think about that and say, okay, 1 times 1 equals +1, and then -1 times -1 equals +1 as well. And those are the only ways that we know how to multiply something by itself to get somewhere remotely close to 1 as a number. So what this is kind of going for is we have to have something new to describe this.
Is that what Mark did wrong though? So is that where Mark's error? So you have the square root of -1 on Elena's side, but Mark just said ignore the negative. I'm just doing the square root of 1, so it's 1 or -1. But you're saying if I take 1 or -1 right here and I multiply them together, I get 1. I don't get -1.
Yeah. So I think that's where the issue is going on. So Elena has an answer that's totally mathematically correct. This is not a number that we really know how to deal with yet. And we're going to have some names for this number and work with this number a little bit. Oh, look. Even the title of the section tells us what we're going to call that number.
It does. So then we're supposed to, so Mark ignored the negative, came up with an answer, but that answer doesn't make sense in the context of this question because if you multiply 1 or -1 by itself, we don't get -1. Then if we consider Elena's solution, does the solution fall within the real number system? So this is part of the work of this section that we're actually skipping, talking about the various different number systems. We're happy to have a conversation with you about what they are, but we didn't want to spend too much time on it because we just don't have that time. So does the solution fall within the real number system? Another way of thinking about that is, can you right now, without knowing anything about whatever this number I is, can you come up with an answer of two numbers, two identical numbers that you multiply together and you get -1 or -4 or negative anything? And your answer is no, because you don't have that knowledge yet. Or you may know about the letter I and maybe you do have that knowledge, but the real number system does not involve the letter I or the number I.
The other comment I want to make about this, because it says talk about using the graph to justify your answer. Based on Mark's setup, he was trying to find the zeros. If this were true on the graph, we would show the parabola crossing through those 2 points, and those 2 zeros would be really visual. I really appreciate the approach to that the authors of this book have taken, because I hate the way that the number I is named. Because it's I because we call it the imaginary number. And it makes it seem like that's not a number that actually exists, and it does. I wish it were called an invisible number because it doesn't show up on a standard graph. Cool.
That's fair. Ooh, let's find out. So in order to calculate the square of any number, it must be some way to calculate the square root of a negative number. That is, there must be a number such that when it is squared, it is equal to a negative number. So if I take a number, multiply it by itself, I need to get a negative number.
Mm-hmm.
Mathematicians defined what is called the number I. The number I is a number such that I squared is -1. That's a big deal. So you're multiplying two things together and you get a negative number.
This is such a big deal that I'm going to write this over here in bright yellow.
I squared is -1. The number I is also called the imaginary identity. So if I squared is -1, then what is the value of I? Well, think about that. How would I solve for I? Do you think they thought about it?
I think so.
Okay. So to solve for I, if we do what was it Elena and Mark on the previous
Hmm.
page? What Elena and Mark did, they took the square root of both sides. So you get I, get to the marker. I is the square root of -1. Now, Mr. Carlson, do we need to put a plus or minus here?
We don't, and that's a really more nuanced question. I knew you were going to ask me that because I is not a variable, so we don't have to worry about that in this context. It's
But we
only,
kind of treat it like a variable, but you're saying it's not a variable.
yeah, and that's why this is a weird thing.
Is that
It,
why we're skipping some of the stuff in this section?
it is.
Okay.
And also, like, for the next step, so I'm going to jump ahead for a second, it asks us to write the zeros of this function. This is kind of what Elena was looking at. So 0 equals x squared plus 1. We end up with x squared equals -1. And this is a slightly different question than I squared equals -1, because x squared is some number that we do not know squared. So now when we take the square root, we have to include the positive and the negative version of the square root of -1, which we could write as the positive or the negative I.
Now, suppose I'm like losing my mind right now and I'm super confused about what you're talking about. Is it fair to say that if I have a negative number and I want to find the square root of it, I just ignore the negative, take the square root, and then put an I there?
So you're saying if I have x squared is equal to -9, if I wanted to find x, I could take the square root. X equals, we need the plus or minus. I know the square root of 9 is supposed to be 3, and because it's negative, I can put an I. Is that kind of what you're saying?
Yeah, because I don't know. Our brains might be freaking out a little bit. Now, the reason you can do that, to give you a little bit of background to that, that's the square root of -1 times the square root of 9. So the square root of 9 we know is 3, and then the square root of -1 we're telling you now is I.
Hey, and that looks like stuff that I was doing in, like when I took geometry and doing the Pythagorean theorem and having to deal with square roots of stuff. And I may have simplified some radicals that time, or maybe not.
No, we do teach them that. I think it's silly, but that's okay. It's important over there. It says the number I is similar to the number pi, even though they are both numbers. Each is special enough to get its very own symbol. There are 3. Is it just 3?
There are 3 that we use all the time. There's
So there
some
are
others
3 that
that,
we use. I, pi, and then there's another number e that you don't know about yet. So that one's pretty fun too. Okay, let's see what comes next. So I think we skipped some stuff here because we went from 4 to 5, didn't we?
but it might be a different 5, I don't know.
Might be a different 5. I deleted some pages in here. I can't remember which ones were which. So we want to talk about imaginary zeros or imaginary roots. How can you tell from the graph of a quadratic equation whether or not it has real solutions or imaginary solutions? Well, is it fair to say, based on what we did at the beginning, if I have 3 different graphs, these were kind of my 3 options. I could have one that looks like this, it hit right there. And the up-down nature of it doesn't matter, so I'll just make them all up. One that looked like that. And one that looks like this. Apparently I used green twice. So those are my possibilities.
So one of the things I wanted to comment on up here is that when we have x squared graphs, we're expecting a certain number of x-intercepts. Because if I draw this curve, and I'm going to take a look at the middle one, I notice that this curve can hit a maximum of 2 times. We've talked a little bit about that with intersection stuff before. It's possible to have it only hit once, or hit no times at all. And that's kind of the weird thing that we're now looking at. So I'm going to say up to 2 zeros. Okay, so now back to the question of which ones of these are real, which ones are imaginary?
The first 2 are real, and the third one's imaginary, based on our graphs from the first page.
And I think it also makes sense kind of based on the way that I've tried to describe this is imaginary zeros or zeros that don't show up on a graph. I can't see my zeros on this graph. Therefore, it makes sense that they are imaginary. All right. The next question, do you think that you can determine the imaginary solutions by examining the graph?
That's a big question. You in terms of coming up with the specific solutions, no, don't even try, because you're not gonna have fun with it.
It's interesting because I'm gonna tell you how this question makes me feel, and it may make Mr. Butterworth feel the same way. I really want there to be some way that I don't know how to do visually to be able to tell you that, oh, this graph has these two specific imaginary numbers. I'm not aware of a way to do that, and it makes me uncomfortable. Because I really want to be able to tell you that there's some magic that we can do without doing algebra. Like looking at this graph and this graph, I can tell you where those zeros are very easily. This one, we can't. There's not a way to do that.
So in terms of explaining your reasoning, I think my reasoning would be, well, when I'm looking for solutions, I'm looking for where the curve hits the x-axis, and this graph doesn't hit the x-axis. So,
Yep, I think that's fair.
I was supposed to delete that page.
Well, we have it listed as an extension. So there was some.
Yeah, but there were statements around this one I deleted.
There were some misunderstandings from some of my students that you do not need to do the work for the extensions unless you want to really push yourself. And then please feel free to kind of dive into that because there are some really cool things here. But we're not going to go there right now.
We can get into this discussion, but we just don't have time to have a full discussion on that. But if you are interested in this, by all means, like this is a kind of cool little family tree type of thing going on here, and we can talk about it, but we just don't have much time. And I thought I deleted it, but I didn't. Okay, so they gave us a worked example there, which I'm going to move over so the kiddos can see it a little better, of rewriting a number. So they said factor out a -1, rewrite the radical, apply the square root, rewrite as I. So this is exactly what we did with that -9.
True.
So we want to do the same idea. So for the first one, we have the square root of -4. So they're saying, take out the -1 and write the square root of 4. And then the square root of 4 I know is 2. And the square root of -1 is I. And I'm done. And Mr. Carlson's following the same steps. Now, notice his order is different than mine. The only reason he wrote it that way, because it doesn't matter. The only reason he wrote it that way is because if he had written the square root of 12i, some of us are lazy with our square roots, and it might look like we're doing this, where we put the square root over the I, and that's a different number.
You would never do that, Mr. Butterworth. You'd always do it.
Definitely would. And so I would take that and put it in front so it doesn't look like it's sliding underneath.
And in both cases, in this case, I did not intend to do that. I just kind of wrote the I first. So thank you for attributing more thought than I had actually applied to that. But in both cases, that would be correct. The other thing that I wanted to note, and I may be putting words in Mr. Butterworth's mouth, that this is totally fine as an answer for me. I think this is totally fine as an answer for Mr. Butterworth as well. If you wanted to go one step further, I will show that as well, which is to rewrite the square root of 12 as the square root of 4 times the square root of 3, because 4 times 3 is 12. And we know the square root of 4 is 2. So we could rewrite this as 2i. We tend to put i's after numbers, square roots of 3.
Mr. Carlson kind of just suggested that square root of 3 is not a number.
Sorry, that we put rational numbers in front of i's generally, and then square roots afterwards because of the aforementioned.
Integers? Can we say integers?
I would not say integers because
rational numbers is fair because you were fractions do it on top. I said corrected. Sounds good.
But as far as you can stop here.
Yep.
It's totally fine if you don't go past that.
By here, he meant right there. I'm making it obvious with the arrows. If you don't want to get to that simplifying square roots, because really the only places you see the simplifying square roots are on standardized tests and cranky college professors.
That's true.
So for C, I'm just going to kind of go to what you could write the answer out as 5 plus, take the negative 1 out, square root of 50. You could break that 50 down, as Mr. Carlson did, into 25 times 2. So if you wanted to, you could write it as 5i square roots of 2. But you don't have to go to that step if that's confusing to you. Just sit here, and Mr. Carlson and I will be quite happy.
Yeah.
And then you did the same thing on D. You just took that negative 1 out.
Yeah, and the reason that they use this as an example, because this is an example where reducing that radical makes this a little bit simpler. But this is, if you're understanding the math to get to here, that's what we're trying to go for. And going further than this, we risk not understanding what you're doing and just kind of canceling things because it looks easier to just cross things out. I'm okay also not reducing that right now on the video because I figure that might be more confusing.
Yes, I concur.
All right. Ooh, we're going to use some technology. That's exciting. Do you want to chat about these while I graph these in Desmos?
Love to. So we've got x squared plus 9, which is similar to the x squared plus 1 we had before. And that one, my guess is we're not going to be able to find. Oh, look, see, it popped up way up there. And then we've got x minus 2 quantity squared plus 1, and that's in vertex form. So I can tell with the x minus 2 quantity squared plus 1 that we have a vertex at 2, 1. My thought is then, if that's an up parabola, I don't know if that's going to hit the x-axis.
Okay, so if I'm looking at 2, so if I'm looking at 2, 1, if I graph that, it doesn't hit the x-axis.
Oh, all right. And then the last one is x squared minus 2x plus 2. That's in standard form. So I can figure out that the y-intercept is 2. And I can also figure out the vertex from that opposite of b over 2a thing that we've done in the past. You don't have to worry about that, though, because Mr. Carlson's going to have it magically show up on the graph. Look, that one didn't hit either. So what do the solutions of the 3 functions have in common? They all have imaginary solutions or imaginary roots. Cool. Because look, none of them hit the x-axis. And that's it for that. So on the next page, we're going to delve more into, and we're skipping because it goes 1, 2, 4. So we're skipping something there. We're going to delve into the x minus 2 quantity squared plus 1. That was in vertex form. Says,
and I think we talked about this one already. And you even talked about what they're asking us to do here.
Right. So use the structure. The structure is we're in vertex form. So since we're in vertex form, and then we also have an up parabola, we can determine there's not going to be real solutions to this. Parabola. So it says, okay, what's the solution? Do you have something to add before we do what's the solution, Mr. Carlson?
No, I just spelled parabol instead of parabola. Oh. So I was correcting my phonics of that as I was talking about that.
Got it. So I'm going to subtract 1 from both sides because remember when we did this originally, we called it, I don't even know what I called it, the squiggle or something.
That's right. You did have
the children will remind us.
A funny word for that.
But anyway, I got rid of whatever that is in there. And this looks just like the Elena and Mark question. So I have something squared equals negative 1. So take the square root of both sides. And that'll turn into plus or minus I over here, just like it did for the Elena and Mark question. And then on this side, we have to just, okay, what is this? And so that was the x minus 2 that was hiding. So it was something squared equals negative 1. Take the square root of both sides. Don't forget plus or minus. And then to finish the problem, we add 2. Now, I'm going to make an intentional choice about where to put the 2. I'm going to put the 2 in front of the I. It just makes me more comfortable to write 2 plus or minus I versus
plus or minus
I
plus 2.
Plus 2. See, that was hard for me to say. Now, if you're scared and if you're confused, what Mr. Carlson has written in the past, we could have written as x minus 2 equals I, x minus 2 equals negative I, add 2 to both sides, 2 plus I, add 2 to both sides, 2 minus I. That's the same answer. But if that makes you more comfortable to write it down twice, by all means, write it down twice if you're concerned you're going to forget something.
Either way is okay.
So then it says, think about, will the graph of the function pass through the x-axis?
And we've already kind of talked about this. I find it interesting that we approach this kind of from that beginning point to then think about the structure of that, which is neat.
So this one says, use any method to determine the zeros of each function. So for us, we could try to factor or complete the square or use the quadratic formula, but I think our purpose is to see what's going on. So the first step is, let's even see if they have real zeros.
So
and if they do, we'll roll with it.
Would that be a good time to like go to Desmos first?
Yeah, so I would go to Desmos and see if they have real zeros or not. And if
right.
they do, I'm going to talk about that. Negative x squared minus 8x minus 18. And it just disappears. So that means we do not have real solutions because we're below the x-axis now. And so we're going to have to do some work to figure out what the solutions of this problem are. There are two more on the page. I'm going to guess that they all have imaginary roots. And so I think we're just going to do one of them because our goal is not to go through all of the factoring, completing the square and quadratic formula over and over and over again for us. So I'm going to go ahead on the first one and complete the square.
That is the method that I would use as well.
Yeah, I love completing the square. So the first thing that makes me uncomfortable is that negative. So I'm going to get rid of it. I'm going to divide everyone by -1. So luckily, there's nothing on the left.
Dividing by a -1 just changes the signs so that they're all positive instead of negative stuff.
That is true. I'm also, in order to complete the square, going to move the 18. And I regret my decision to not leave space there, so I'm going to go back and make some space. So now I left an empty box there. And into that, we're going to have to put what number makes it so that we can factor this into x plus 4 squared. Now, if you're wondering, whoa, where did you get the 4 from? To remind you, divide the 8 by 2, that's where I got the 4 from.
Yeah, because we want to break that into 2 equal pieces.
Yeah. And the number in the box is going to be 16.
Oh, because if I did 4 squared, that would give me 16.
Right. If you wrote down x plus 4 times x plus 4 and double distribute that, you get the plus 16.
And if we add that on this side, we got to add that in the other box as well.
Yes. So then I get a -2 on the left. Now I have something squared equals a number. So I take the square root of both sides. So I get the square root of -2. Don't forget plus or minus. X plus 4. And then my last step, I'm going to do two things at once. Don't freak out. It'll be okay. Keep breathing. I'm going to subtract the 4. I'm going to put the plus or minus, and then there's a negative in that square root. So I'm going to make an I appear in square root of 2. That's all there is there. So if you're getting comfortable with completing the square and quadratic formula stuff, cool. By all means, keep using those things. If you're not, it's okay. We will figure out kind of how we want to make sure you're paying attention to this. Remember, we're going to be looking at how things are built and the solution and, focusing on the method there.
All right, and then I've got some stuff that looks like it's expected for them to try on their own.
Yeah, I would say B and C, give it a shot. Feel free to put it in Desmos and see if there's a real zero, and if there is, cool, and if there's not, that's okay. And if you want to try to solve them using whatever method you want, if they're not real zeros, you're not going to be able to factor it, just as a heads up. But completing a square or quadratic formula, go for it and try it. And if you get an answer, awesome. And if you don't and you're struggling with it and you want to talk to us about it, cool. But that is all we have for you today, because after this is the talk, and then the assignment.
I like it.
That's a good talk, too. So we'll spend some time in class talking about that.